All right. So back up here, this is just our definition of logs, right? We have a sentence in exponent form, and we can say the same thing in log form, okay? So for every exponential expression, there's a log expression that matches it, okay? And then over here, this just gives us like restrictions, saying our base can't be negative, it can't be 1. Same thing for our argument has to be positive, okay? Okay, now for every exponent rule, there's a log rule, okay? So I'm just going to write down the cousin, a to the m times a to the n, okay? So back in our exponent properties, when we were multiplying powers of the same base, remember what we did with those exponents? We add, subtract, multiply, or divide. What do you do with these exponents? Add them, yeah. So what we learned is that when we're multiplying arguments, we add exponents, okay? Well, coming over here to a log expression, if I have the log of a product, so this is the argument, so if I'm multiplying arguments, I'm going to add exponents. And logs are exponents. So this equivalent statement would be log base b of m plus log base b of n. Because logs equal exponents, so this is like saying I'm adding the exponents whenever I'm multiplying the arguments. It's the same property written in terms of a log instead of an exponent. Okay? Now the quotient property, this is related to this exponent rule where we would divide powers of the same base. Remember what we would do there? We would subtract those exponents. So when we are dividing arguments, we're subtracting exponents. So if I come over here, this is my argument, so I would subtract the exponents, or in other words, the individual logs. Okay? And then this last property is a little more difficult for me to explain, but whenever we took a power to another power, so something with an exponent raised to another exponent, we multiplied those exponents, okay? Well here, log base b of a, this represents an exponent. Log base b of a is an exponent. And then look what we're doing. We're taking that to another power of p. So we would just multiply these. And here's how I would write it. P times log base b of a. So all of these properties are cousins of the exponent property. Okay, now why do we care? Why do we need to know these? Well, because these can help us simplify an expression if we get stuck. So for instance, all of these in example 2. Express as a single logarithm. Simplify. Okay, so log base 6 of 4. Log base 6 of 4. 6 to what power makes 4? Well, I mean, you can look at your power chart, and we can find 6, and we're not going to see 4, okay? So you could say that, okay, we're stuck. But I notice that they're added, so if I have separate logs that are added, if I put them together in one log, we can take those arguments and we can multiply them. So I can take the arguments of 4 and 9 and I can multiply them. Let's see if that helps us. What is 4 times 9? What's 4 times 9? 36. Now, does this have an answer? 6 to what power makes 36? Well, 6 times 6 is 36, but 6 to what exponent gives you 36? Because remember, logs equal the exponent. So this is asking us, what's the exponent here? 2. Yeah. Because 6 to the second power is 36. So this expression just equaled 2. Okay? Which we never would have been able to do if we hadn't used this property. I have a little typo in B. Okay? I'm sorry. I have a little typo. Scratch out that plus sign and change it to a minus sign. Okay? I want that one to be a minus. Because if it's a plus, then I got to multiply 36 times 12, and I don't want to do that. Okay? So this one, same here. Log base 2 of 36. Well, if I look at my powers of 2, I can't get to 36 by taking a power of 2. Okay? So I can combine these into one log. Log base 2 of, now what can I do with these arguments? That's my quotient property. I can divide them. So I can say this is 36 divided by 12. Okay. Now 36 divided by 12 is 3. So this is going to be log base 2 of 3. Now, I can't figure that out either. 2 to what power is 3? Not a nice power. So I'm not going to go further like I could here. This is just my final answer. Because the directions told me express as a single logarithm and then simplify. Okay, you guys try part C on your own. There's nothing crazy about it. There's no typo. It's all good. You try that one. Okay. This one will simplify all the way down, right? You'll be able to get a number answer for this one. So, when we put these together, since when they're separate logs at subtraction, when we put them together, we're going to divide the arguments. So it will be 100 divided by 4. And then 100 divided by 4 is just 25. And log base 5 of 25 equals what? 2. Because 5 squared is 25. So sometimes we'll be able to simplify all the way down and sometimes not. But condensing is in order to solve an equation, so like in a couple days, we're going to put an equal sign and put stuff on the other side. In order to solve, we need to have log written one time. So we're just practicing being able to do that. Okay, example 3, express as a product, simplify. Well, why is it telling me that? It's telling me to use this property. Okay, if I have a log of something to a power, I can bring that power in front. Okay, so I can take this power and plop it in front of the log and multiply, because that's an exponent and the log is also an exponent. So I say this is 6 times log base 2 of 32. Okay, so we've done that. We've expressed this as a product. Now if we can simplify, we should. Can we simplify log base 2 of 32? Can I rewrite 32 as a power of 2? Yep, right here. Right? 2 to the 5th power is 32. So this is 5. Log base 2 of 32 is the number 5. And then we can do 6 times 5, right? 6 times 5 is 30. So that equals 30. Okay? Doing that with b. Express as a product. I have a log, and then it has an exponent, so that exponent gets to come in front of the log and be multiplied. So 4 times log 10. Okay, now remember, if you don't see a base, what is it? 10. So I could write that in if needed. 10 to what power makes 10? Just 1, right? So this would be 4 times 1, and 4 times 1 is 4. So using these properties help us to easily simplify some expressions. Okay? Questions so far? Okay, let's look at 2 other properties. We got change of base. Okay? And there's nothing for you to write in this little box because I put it right here. I just didn't want it to get copied down wrong, so I just put it right here. Basically, this is saying if you don't like the base of a log, you can change it. Perfectly legal. You can change it to anything you want, provided it's, positive and not equal to 1. You can change it to anything you want. You just have to take log of whatever your new base is of the argument divided by that same log of the base. Okay? This will make more sense when we actually apply it. Coming over here, inverse properties of logs. Let's see. Now these 2 kinds of expressions are special, and if we recognize them, we don't have to do much work. So log base b of b to the x. What does that mean? Well, if you think for a second, if you take x out of the exponent and plop it in front, it looks like log base b of b. X times log base b of b. But no matter what b is, log base b of b, what will that always equal? What's the exponent? B to what power gives you b? What would be the exponent there? Just 1, right? So no matter what b is, this thing right here is always going to equal 1. So x times 1, this is just x. So what we learn here is that we don't have to do this power rule every time. If I recognize that I have log base b of b, those just cancel. They're inverse operations of each other. They cancel, and your exponent is just your answer. Okay? And the same thing is true when we reverse it, when we have a base of an exponent and we raise it to a log, which is weird, but it happens. That also cancels, and we're left with x. Okay? This is also eventually how we're going to solve equations. Okay, so now we're going to practice using either or both of these properties. Okay? All right, I want to simplify log base 4 of 32. And if I look at my power chart for powers of 4, 32 is not a power of 4. Okay? So, you know what? I don't like that base. I want to change it. And I can change it to anything I want. Let's think about 4 and 32. Let me get my power chart back out. Are 4 and 32 powers of the same number? Can I write them as powers of the same number? Yeah. 4 and 32, they're both powers of 2, right? Okay, so here's what I'm going to do. I'm going to choose my new base to be 2. So I'm going to use the change of base formula, and the new base is going to be 2. So I'm going to write log base 2, and then I have to put the argument up top, so 32, over log base 2, and then I put my original base on the bottom, and that one was 4. Okay? So I'm just plugging into this formula. Okay, now I want to use this. I'm going to use the inverse property. So 32 is 2 to the 5th power. So I'm going to write log base 2 of 2 to the 5th power. Got to be careful. You've got all kinds of levels here. You've got a subscript, a regular number, and an exponent over log base 2 of 2 to the 2nd power, because that's what 4 is, right? Is everyone okay with where I got these? Okay. Now, I can use this little inverse property to kind of cancel some stuff out. Log base b of e. Look, I have log base 2 of 2. That part cancels. I got another log base 2 of 2. That part cancels. So what am I left with? 5 over 2. And that is my answer. It's just 5 over 2. Okay? So we can change, if we don't like it, we can change it. So log base 27 of 9. 27 to what power makes 9? I don't know. I don't like that base. So what might I use as a common base for 27 and 9? We can write 27 and 9 both as powers of 3. So that's my new base. I want the base to be 3. So we're going to write this as log base 3 of our argument over log base 3 of our original base, 27. Okay, now I'm going to rewrite 9 and 27 as powers of 3. So log base 3 of 3 squared over log base 3 of 3 cubed. We got all the levels of 3. Now I have my inverse property, right? So cancel, cancel. And what am I left with? 2 over 3. Okay? Does that make sense? Okay. Let's try C. We have 8 and 1/16. I don't like it. So I got to think, all right, 8 and 16. Those are both powers of 2. I know 1/16, that just means a negative exponent, right? So let's write these as powers, or I'm sorry, with a base of 2. So this would be log base 2 of the argument, which is 1/16, over log base 2 of 8. So we have log base 2 of 2 to the power of, well, 2 to the 4th is 16. So to make 1 over 16, it must be a negative exponent. So negative 4 over log base 2 of 2 to the 3rd, because 8 is 2 to the 3rd. Okay, then we got cancel, cancel. Final answer, negative 4/3. I don't really know where I could put that, so I just squeezed that back up there. Negative 4 over 3. Okay? Okay, one more. Now we have 1/4 and 64. So there are 2 ways we can do this, because 4 and 64 are both powers of 2, but they're also powers of 4. So I'm going to use 4 as my new base. So I want to use 4 as my new base. So this is going to be log base 4 of 64 over log base 4 of 1/4. Okay. Log base 4 of 4 to the 64 is 4 to the 3rd power. And then log base 4 of 4 to the -1 to make 1/4. Cancel, cancel. Woo! And we're left with 3 over -1. That's an equal sign. And 3 over -1, can't we simplify that to just be -3? Okay? So you might be wondering, well, how do I know when to use this formula? You use the formula when you're told to simplify a log that won't work with your power chart. If it don't work with the power chart, then you got to use this. Okay? Okay, now look at this one. 3 to the log base 3 of 5. Now that is this, also this is an inverse property. Base, base, match, they cancel. Okay? So that cancels, this just equals 5. These are really simple. 4 to the power of log base 4, that part just cancels. This one is just 7. Okay? ln of e to the 3rd. Got to remember, what's the base of an ln? It's e. So these match. 3 is just our answer. And then e to the ln, those match. Okay? So this is just about recognizing when you have that inverse property. Okay? And like I said, it's going to come back more when we are solving equations. Okay. Now we're going to go back to the properties from the front. Write each expression as a single logarithm. Okay? So we want to, end goal, we want to write log one time. Okay? So you kind of follow PEMDAS here. You do the multiplying and the powers before you handle addition and subtraction. So if I have, see how I have this 3 in front of the log? These don't cancel because this is 3 times a log. It only cancels if I'm taking a log base 3 of 3. So nothing cancels here. But if there's a number in front of the log, that is this property. Okay, so what we can do is we can take that 3 and pack it back up as the exponent on the 2. And that's the only exponent situation that we have in this expression. So I'm just going to do that in my first step. So this is log base 3 of 2 to the 3rd plus log base 3 of x minus log base 3 of 37. Okay. Now I have addition and subtraction. If you remember from PEMDAS, you do addition and subtraction from left to right. Okay? So I'm just going to handle the first 2 logs. Okay? If I'm adding them, I would multiply the arguments when I put them together. So I'm going to put these together. Log base 3 of 2 to the 3rd times x. And then I have minus log base 3 of 37. Everyone okay with where this came from? So I'm just dealing with these, putting those together. Okay, now 2 to the third, can we all understand that that's 8? Because in my next step, I'm just going to convert that to 8. All right, now I'm down to 2 logs, and they're being subtracted. So when I put them together, we're going to take the arguments and divide. Okay? So what am I going to divide? 2 cubed x over 37. So log base 3 of, and 2 cubed is 8. So I'm just going to write that as 8x over 37. Okay? So these are equivalent. This is just condensed into 1 log, and this is expanded into multiple. Okay? Okay, let's do that here in B. Now we have natural logs. Okay, but we're going to follow PEMDAS. So if we have any numbers being multiplied to our logs, we're going to put that number back as the exponent. So I have that here, right? That's going to go back up there. And then I see this 5, that's going to go back up and be the exponent there. So we have ln of 4 squared plus ln x minus ln, x to the 5th. Sorry, my x looks weird. So all I did in this first step was put those exponents back up. Okay, now all I have is addition, subtraction, so I do that from left to right. So I start with these, separate added. When we combine them, arguments get multiplied. Now, can I convert 4 squared to 16? Are we all okay with that? So that'll be ln of 16x minus ln of x to the 5th. Okay, I'm down to 2 logs. So when I when I combine these, I'm going to divide the arguments. So 16x over x to the 5th. And technically, we can simplify that a little further. We can cancel out an x, but I'm not going to worry about that. Just going to leave it like this. Okay? So we did our job. We wrote as a single logarithm. Okay? I know, we just have to practice those properties, and we'll get a chance to do that. All right. Last thing we got to talk about are the logs that just do not work nicely. Okay? So log base 4 of 30. 4 to no power I can think of makes 30. And then if I look at my power chart, I can't rewrite these as powers of the same base. Okay? So what do? Well, we need a calculator. Okay? Back in the day, this calculator here, maybe you have some, there was only a log button and an ln. And because of that, those are the common bases we would use, because those are the only buttons we had on the calculator. So I can choose a common log as my log. So I could say this is log 30 over log 4. And then I'm just going to have to type that in, right? Because I can't make that, look nice. So if I come over here, I can type log 30 over log 4. And I can get my decimal that way. 2.453. Okay. Now it also works with ln. The other button that we had on the calculators was the natural log. So I could use ln. So I could say this is ln 30 over ln 4, and it is going to give me the equivalent Okay? ln 30 divided by ln 4 gives me the exact same decimal. So it doesn't matter what the common base is. Okay? Now, today we have Desmos, and Desmos is better than those calculators in many ways. Okay? Desmos will let you actually type this in, log base 4 of 30. Okay? The way you type it is, well, you can go down here and you can go to functions and you can find log. I think that's a lot of work. You can go log shift minus sign 4 of 30, and it gives you the exact same crazy decimal. Okay? 3 different ways of doing the same thing. Now, which way, should you use? It does not matter to me, except if the directions are very specific. So if we look in number 8, write the logarithm as the quotient of 2 common logs. Leave the answer in exact form. Okay, so something I need to point out is this and this are considered exact form. When you put the decimal, that is an estimate. So this question is telling me to use common log. So if it's telling me to do that, I need to do that, right? So I would write this as log 32 over log 6. And it says leave it in exact form. All that means is I'm not going to type that in the calculator. I'm just going to leave it as is. That's exact form. Okay? So when do we have to use this? When we can't figure out the log and when we can't do it by changing our base on the power chart. The ones that are really annoying, that's where we need to do this. Okay? I'm going to skip example 9 because it's just typing in the calculator and ordering least to greatest. I don't necessarily think that's the best use of our time, so I'm just going to skip it. Okay? If you're dying to know what it is, the Schoology copy will have it on there.